உங்க ப்ரோக்ராம் எவ்வளவு நாள் சார் இங்க போர்ச்சுகல்ல?
எனக்கு 3 years சார். ஆக்சுவலி இப்போ நான் ஊருக்கு வர்றது வந்து என்னோட கான்ட்ராக்ட் கம்ப்ளீட் ஆகி தான் வரேன் நான். நெக்ஸ்ட் வந்து இப்போ சம் ப்ராஜெக்ட் எல்லாம் அப்ளை பண்ணியிருக்கேன்.
அப்படியா? சரி சரி.
ஆமா ஆமா, அது அடுத்து இன்னொரு ஷார்ட்டா அடுத்த ஒரு ப்ராஜெக்ட் வரப்போகுது. ஸோ நெக்ஸ்ட் அது முடிஞ்சு எனக்கு ஒரு பர்சனல் ரீசன்னால நான் கொஞ்சம் ஸ்டே பண்ண வேண்டியதும் வருது இந்தியால.
சரி.
ஸோ ஆல் டுகெதர் எனக்கு அது கொஞ்சம் கரெக்டா இருக்குது.
ஓகே ஓகே. Dr. Edwin sir, good evening.
Very good evening. How are you?
Welcome sir, welcome sir.
Good evening.
Yes sir, good evening. Sabari sir, we'll start at 5:35. The people are joining. Just we'll wait for 5 minutes.
No problem, no problem.
Karupusamy sir, good evening. Dr. Karupusamy, good evening.
देखना बिठाना
Dr. Titus, good evening.
Sir, good evening, sir. Good evening, sir.
Welcome. Sabari sir, he is Dr. Titus. He is assistant HOD at one of our engineering college here, local private engineering college.
Okay, sir. Hello, sir.
Hello, sir. Good evening, sir. Welcome you, sir.
Thank you, sir. Thank you.
Ramakrishna College of Engineering.
Okay.
After Samayapuram.
Titus sir.
Yes, sir. We'll start, sir.
Titus sir, good evening.
Sir, good evening, sir. Good evening, sir.
என்ன காலேஜ் எல்லாம் இருக்கா இன்னைக்கு? காலேஜ் எல்லாம் இருந்ததா?
ஆமாங்க சார், காலேஜ்ல இருக்கு.
Okay. Thank you.
Okay, sir. Thank you, sir.
Sabari sir, we'll start. Others let them join.
Okay, sir. Okay.
Yes, sir. Happy good evening to everyone. Today we have an interesting webinar topic. There is Oxitic Metamaterials, which is going to be delivered by an eminent personality, Dr. Sri Sabari Sanmugam, investigator, University of Coimbra, Portugal. First of all, we from IEI Tiruchinnappally Local Center and with other participating 5 associations, thank Dr. Sri Sabari Sanmugam for readily accepting
Sir,
our
voice
invitation.
break ஆகி வருது போலங்க சார்.
Break ஆகி வருதா? Yeah. Okay. Now it's okay, sir. I'm audible.
Yes,
sir.
yes, you are audible.
Okay. Thank you. Happy good evening to everyone. Today we have an interesting topic. That is the Oxitic Metamaterials, which is going to be delivered by Dr. Sri Sabari Sanmugam, investigator, University of Coimbra, Portugal. First of all, we thank Dr. Sabari Sanmugam for Sri Sabari Sanmugam for readily accepting invitation to deliver a webinar to our members today. We are very much welcome you, sir, Dr. Sabari, for our weekly technical program, sir. Thank you, sir. Yes, sir. We Tiruchinnappally Local. Thank you, sir. We Tiruchinnappally Local Center conducts weekly technical program for the past 3 decades. Before the pandemic, it was in physical mode. It was conducted in our IEI Tiruchinnappally Local Center office, Dr. APJ Abdul Kalam AC Hall, with the 100 seating capacity situated in BHL 3000 acres campus. After the pandemic, we switched over to the virtual mode. That is, today it is 120th program. The main advantages of going virtual is today we are able to call Sabari sir to deliver his expertise with us, and also participants all over India and all over the globe. We IEI Tiruchinnappally Local Center is a role model in conducting technical events in our campus among the 10 active professional institutions situated in our campus. We have another auditorium with 300 seats capacity. We conduct seminars, symposium and all that. We conduct weekly technical programs, state and national workshops, conferences, conventions in all the 15 disciplines. We also try to have the corporate members of 2,400 with the student members of more than 7,500 who are pursuing our AIME examinations. As a corporate India, as overall India, we have more than 230,000 members with more than 125 centers throughout India and abroad. Some 6 centers are there. We propagate and disseminate emerging technologies from the eminent personalities to our members from education institutions, students, industry experts of various engineering colleges students, and to the society. We IEI Tiruchinnappally Local Center boundaries from Ariyalur, Perambalur, Karur, Pudukkottai up to Nagapattinam, except in Tanjavur district. We IEI support education institutions in conducting seminars, symposium. We also provide R&D fund and all. With this note, I call upon our past chairman, engineer Dr. Karupasamy sir, for proceed and welcome the gathering, sir. Over to Dr. Karupasamy. Karupasamy sir, please.
Hello.
Yes, sir. Please, you are audible.
Am I audible?
Yeah, you are audible, sir. Please go.
Hello. Good evening to all. Hello.
Yes, sir. Go ahead, sir.
Good evening to all. At the outset, I am very happy to be with you in today's webinar presentation on Oxitic Metamaterials. The speaker, Dr. Sri Sabri Shanmugam, who is readily accepted our invitation and going to present a new topic today on Oxitic material, which is a new material and invented for newer and special applications. I think the participants are going to be benefited by his presentation in the next 1 hour. I thank and also welcome all the participants and especially welcome the speaker, Dr. Sri Sabri Shanmugam, who is going to present a newer topic. Thank you. Thank you.
Thank you, Dr. Karpusar, for a nice welcome address and also welcoming the gathering. Also telling the importance of the new material. Now I call upon our committee member, Engineer B.V. Kandasamy, our committee member, to introduce the speaker to the audience. Over to Engineer Kandasamy, sir. Please, sir.
Good evening, sirs.
Welcome, sir.
I'm extremely happy to. Sir, am I audible, sir?
Yes, sir. You are audible, sir. Please go ahead, sir. Please.
I'm extremely happy to introduce Dr. Sri Sabri Shanmugam, who is working as postdoctoral researcher in the Department of Mechanical Engineering, University of Coimbra, Portugal. He did his Bachelor of Engineering in Mechanical from Francis Xavier Engineering College, and he did his Masters in Engineering in CAD/CAM in Kungu Engineering College, Erode. He also did his MBA from Badia University, and he completed his doctorate in Manufacturing Engineering from Annamalai University, Chidambaram, which is recognized by the University of Coimbra, Portugal. Thereafter, the University of Coimbra has awarded him for 2 postdoctoral fellowships from 2016 onwards. He also worked as full-time researcher in the Center for Material Joining and Research, Department of Mechanical Engineering, Annamalai University. He worked as junior and senior research fellow in the Department of Mechanical Engineering, Annamalai University, in the DRDO sponsor project. He has some teaching experience also. He worked as associate professor and assistant professor in Sri Vidyaniketan Engineering College and Starline Engineering College of Engineering and Technology, Tanjavur, for about 3 years. He has developed a technology in the field of underwater friction stir welding process through a project titled Evaluation of Fatigue, Fracture Toughness and Ballistic Performance of Friction Stir Welded AA2519-T87 Aluminum Alloy, which is adopted by the Defense Metallurgical Laboratory, DMRL, Defense Research and Development Organization, DRDO, Government of India, Hyderabad. To his credit, he has got a lot of awards and honors. He received D.N.H. Sesharan Award for the best paper presentation. A paper titled Experimental and Numerical Investigation on Underwater Friction Stir Welding of Armor Grade Aluminum Alloy was listed once as the most downloaded article, secured 8th place in the Defense Technology Journal Elsevier publication during 2017. He was also awarded with Early Career Research Award as the principal investigator for the project. His PhD thesis was recognized by Government of Portugal during January 2019 and awarded with postdoctoral fellowship from the Foundation for Science and Technology, Portugal, for the project title Sustainable Built Environment and Natural Hazards and Extreme Events. Award of postdoctoral the same foundation for the project titled Modeling and Control of Friction Head Heating, Friction 4.0. He has published 18 papers in international journals, which is cited more than 230 times. His conference presentation is also the life member of Indian Welding Society. He has guided so many projects, student level projects, in undergraduate projects, in the number 8 projects he has guided, and 3 postgraduate projects also are guided by him. His area of interest is additive manufacturing, material science, manufacturing technology, material characterization techniques, mechanical testing, CAD/CAM, and finite element analysis. I am extremely thankful to Dr. Selvaraj for giving me an opportunity to introduce such an eminent personality. The floor to you, sir. Thank you, sir.
Thank you, Engineer Kandasamy, for a nice introduction. Thank you so much. Thank you for sparing your time with us. Thank you.
Thank
Now
you,
over to Engineer Dr. Sri Sabri Shanmugam, sir, for your presentation, sir. We are looking forward to hear you, sir.
Okay.
Yes, sir. Please.
Okay, first of all, thank you for your wonderful opportunity to do the presentation here in a big forum. And nextly, I would like to thank Kandasamy sir for his wonderful opening about me. So let me continue my talking by presenting this topic, oxitic metamaterials. So before going to the to see about this topic, let me explain about what is oxitic metamaterials. So oxitic means it is a term derived from a Greek word called oxito, which means increasing. And the meta is another Greek word. It is derived from a Greek word, namely beyond. So it's something it's explaining about increasing and beyond. So a material which is going to perform with an enhanced way. So it's called as oxitic material. So it's not a real material. It is a material which is having a better property. So I will explain about this in the coming slides. First, before knowing about the oxitic metamaterials, we should know about what is meant by Poisson ratio. So because this oxitic material is a special materials which is exhibiting a special, unique Poisson ratio. So we are going to see about that. Since we have engineers from various fields, I need to put some basic introduction about this Poisson ratio in order to bring them to the topic. So we all know about this chocolate, which is very famous during 80s and 90s. So we might have experienced the tastiness of this chocolate, or at least we used to buy this for our kids. So after eating this chocolate, we used to do one thing. We will expand this. We used to play with the wrappers. We used to expand it. And two kids will used to play to expand it in both directions. And the game will be like who will get the most portion of the wrapper. So this is the idea of this game. So here you can see that, consider this as a wrapper. You are extending in both directions. So what is happening in the center of the wrapper? The thickness of the wrapper is getting reduced. So the reduction in that thickness will be in both direction. It will be compressed in this way as well as in this way. So you will have a reduction in the cross-sectional area. So if you see the if you section that region and if you see the area, so it get reduced. So this is a well-known factors about phenomena about the deformation how happening there. So with that idea, we will see what is the Poisson ratio. So here in this figure, you can see that when you are pulling a material, namely it may be a steel or it may be any material, what is happening here, when you are pulling it in both directions, you will encounter a reduction in cross-sectional area. On the other hand, if you compress the material, what will happen? You will have an expansion in the cross-sectional area. So you will have an expansion in the center region. So with this expansion and contractions, the Poisson ratio can be explained as negative of ratio between lateral strain and longitudinal strain. So strain is nothing but, we can calculate it from this equation. It's the ratio of changing length divided by original length. So in this case, you can see that, for example, this is X direction and this Y direction. So you will have a change in the dimensions. For example, if you have it 10 centimeter, after pulling it will become a 15 centimeter. I found some disturbance from organizer. Could you please mute that person?
Yeah, Mr. Rajesh. Rajesh, kindly mute the sounds are coming, please. Rajesh. So Rajesh.
Okay. So, for example, the length is 10 centimeter. So on pulling, it will become a 15 centimeter. And in the contraction, in this direction, you consider it is having a 5 centimeter. So it will change to 3 centimeters. So there is a change in a dimension is there. So the change in length divided by the original length. So change in length is nothing but the difference between the final length to the initial length. Okay. So with these equations, you can calculate the strain, and the strain can be used here to calculate the Poisson ratio. So the Poisson ratio can be mathematically represented in this way. And coming to this, we have two terminology. One is positive Poisson ratio, and second one is the negative Poisson ratio. So positive Poisson ratio is the conventional one, what we see everywhere in the engineering systems. Everywhere, not only the engineering system. If you take the chocolate wrapper, you can see the positive Poisson ratio. But there is another concept called negative Poisson ratio. So what will happen in negative Poisson ratio? So in this figure B, you can see the schematic representation of the negative Poisson ratio. Here you can see that if I pull a material, the material will try to expand, which is conversely to the positive Poisson ratio. So here, if I pull a material or push a material, an inversional thing is happening here in the cross-sectional area. Whereas in the negative Poisson ratio, if you pull a material, you will have a similar thing. So here, an increase in length is happening in this direction, as well as an increasing in length is also happening in this direction. In this case, the diameter is increasing. So this is a negative Poisson ratio. Just think, in this case, if instead of a compression or instead of a reduction in this cross-sectional area, if you have an increase in cross-sectional area, will the game end soon? No, the game will extend, which means the failure will extend, which means the material or the structure will remain for longer time. So this is the thing is going to make a new thing. So coming to here, if you see the various engineering materials in the practice, you can see foams, cork, rubber, plastics, and other materials like steel, carbon fiber. So in these materials, you can see that the Poisson ratio value is lies between 0 to 0.5. So if you are a mechanical engineer, you might came across a lot of calculations for the for understanding the stress or strain or know about the stress distribution. You must come across the Poisson ratio value, and we used the Poisson ratio of 0.3. So for the metals, most probably it is 0.3, and it lies plus or minus like 0.05 or 0.0 plus or minus 0.05. So if you see the steel, the 0.3 is the Poisson ratio. But just see the left portion of this graph, it remains vacant. So there is no material here which is having the negative Poisson ratio. So if we explore some kind of material over here with a negative Poisson ratio, we can increase the life of the material, or we can increase the performance, or increase the properties, or whatever the thing, we can do that. So in the theoretical prediction of Poisson ratio, the classical mechanics theory is saying that the Poisson ratio values lies between minus 1.0 to 0.5. These are the general one. But there are some exceptional, very rare cases are there which may have a more Poisson ratio here. Some of the researchers performed some tests to find Poisson ratio more than 0.5. Some foams have that value, and there are some materials having this negative Poisson ratio value. So that we are going to see about that. And coming to another thing, you can see that there are two extremes there. So here the cork is an extreme one, where you can find the cork in various applications. Most probably we know that the cork is over the wine bottle, and in the rubber, you know that. So here the Poisson ratio 0 represents that when you are applying a force at one direction, the lateral expansion or contraction will not be there. So that is the idea. If the Poisson ratio is 0, so there is no lateral or lateral contraction or expansion. Whereas in the rubber, if you apply a pressure from one direction, in the lateral way, you will have a major expansion or contraction. So if you have a higher Poisson ratio, you will have this. And if you have a lower Poisson ratio in the positive system, which is 0, it's neither positive or negative, if it's near to 0. So you won't have any kind of thing. So with respect to the this expansion and contraction, we can see lot of applications. Okay. Okay. Coming to the scientific database. So Scopus is a scientific database which we can see the number of research or amount of research published in particular area. So the figure shows the publications, number of publications with respect to the year. So you can see that this oxitic material gets started, attention, in 2001. Actually, it was founded well before, but the researchers got notified this from the year 2001, and it gets rapidly increasing to now. So still it is going on. So this proves that this material is having a lot of potentials for various applications. Okay. Okay, so coming to this Poisson ratio, you can see that as I told that the Poisson ratio is going to enhance the property. So how this is possible? What are the things that are happening there when you are using an oxitic material? Okay, so first one is the bulk modulus. So the Poisson ratio have a lot of relationship with other properties or other characteristics of the material. So by increasing the Poisson ratio, in turn, it increases some other property of the system, and it increases the performance of the material or performance of the structure. So what are the relationship and what are the parameters are closely associated with this? Okay, as we know that in order to describe a material, we used to describe the material with respect to strength. For example, if you are going to select a material to fabricate a car, so the very first thing is we will think about how strong it is, how tough it is. So these are some of the characteristics we are going to talk. So so we should know about what are the properties of the material. So the bulk modulus is one of the important properties which will be selected when we are designing a structure. Okay, so it plays a major role in the material selection. So bulk modulus, what is bulk modulus? So in this figure, you can see that a schematic expression of the bulk modulus. So you can see that the bulk modulus quantifies the resistance of the solid to volume change, which means if you are applying a force either in the compression or the tension, how much the volume change is happening there. So if a material exhibit higher bulk modulus, it won't change its volume. The change in volume will be very limited. Okay, so that's the idea. So here you can see that the bulk modulus have a relationship with the Poisson ratio here. So this symbol nu is the representation of the Poisson ratio. So here you can see that the K is equal to E is nothing but the Young's modulus. It is a relationship between the stress and strain in the elastic domain. Okay, so it is a ratio between that. So E divided by, we will have the Poisson ratio here. So this is one relationship with bulk modulus. So we can understand that if you change this Poisson ratio value, we will have a change in the bulk modulus. And the second property which decides the material performance is the shear modulus. So the shear modulus quantifies its resistance to volume, preserving to shear deformation. So shear is, you know that this is the shearing. Okay, so in the face, you are applying the force in this way, which tends to create a shear deformation there. So you can see this dotted line is the original structure, and the gray region is the gray model is the deformed structure. So here you can see that you will have a change in dimension of this delta X in these directions. Okay, so here the same dimension changes, will be there. Okay, so here you will have a delta X, and here you will have a delta X here. Okay, so the shear modulus, I can say that if you are having a higher shear modulus, the material will offer higher shear resistance to the deformations. Okay, so here also the resistance against the volume will be there. So the shear modulus here, it can be related with the Poisson ratio in this way. So here we can understand that this Poisson ratio is also a function of shear modulus. Okay, so in the previous slide, I said that the values of the Poisson ratio will changes from -1 to 0.5 in general. So let me explain by putting the value from that. For example, if I am putting a value 0.5 here, what will happen? So if I am putting 0.5, so in the 0.5, I can say that instead of 0.5, I can put like 1/2. So 1/2, if I invested here, it will have 1. 1 minus 1 is 0. So we will have an infinity there.
Breakthrough in talks in Istanbul. Moscow's negotiators getting that news right now. Sean continues to be with us on Big Story. We're also being joined by Botan Nahailo, the acting chief editor of the Kyiv Post. Mr. Nahailo, your first reactions to the developments out of Istanbul right now. Do you believe these are...
Mariamuthe, Rajesh, there is a disturbance. Please mute.
They say they are pulling back from Cuban Chernihiv. They still want to occupy Crimea and all of the Donbass. They are invaders. They are.
Okay, thank you. Okay, so here you can see that if I am investing the 0.5 in the place of Poisson ratio, you can see that this K will go to an infinity. Okay, and if I am placing 0.5 here, you will have a lower shear modulus. Okay, so which means if the Poisson ratio is positive, you will have a higher bulk modulus and lower shear modulus. And in the other hand, if I am investing -1 in the place of Poisson ratio, what it will happen? So here you will have a different bulk modulus, but particularly if you notice the shear modulus, if I am investing -1 here, what will happen? So 1 minus 1, it will become 0, and the shear modulus is going to increase. So this is a very much wanted property of the negative Poisson ratio. So it means that the material become difficult to shear, but easily deform volumetrically. Okay, so by using this property, you can tailor a lot of other properties for different applications. Okay, so coming to this oxitic material. So as it told in the very first slide, this oxitic material, it's not a real material like a metal, polymer. We know about a lot of material type, you know. We have metal, then we have composites, then metal, we have different types of metals are there, steel, aluminum, and we have composites, we have metal matrix composites, polymer based composites. So here the term materials doesn't represent that the type of material, rather this material is the material represents the geometric feature. Okay, so I can explain in other words that this is one of the oxitic material which can be made using steel or polymer or composites or ceramic or whatever may be. So someone on hearing this word oxitic material, they will initially confuse, oh, this may be a new material or a novel material. This is not material type. This is not the case. So this oxitic material is the term related to the geometry of the material. So here you can see that there are different forms of geometries are there here. So here the first one is called the re-entrant structures, where you can see there are re-entrant corners. Okay, so these are all the cellular-like structures, which are periodically arranged in a matrix, and the global structure is called as the oxitic material. So this one cell is called as a unit cell, and arrangement periodically in a regular way will create a complete structure. So this structure is called as the oxitic structure. So it's not any kind of alloy type or the material type. So these are all the conventional oxitic materials that can perform in a better way. So the first one is the reentrant structure, and second one is the triangular. You know about this triangle. It is arranged accordingly to give the negative Poisson ratio. And then the next one is the star, the next one is the square, and we have a chiral structure. So these are all the conventional geometries which will yield the negative Poisson ratio. There are other structures are also there. For example, these reentrant structures can be modified into hundreds and thousands of structures, and this triangle you can modify into hundreds and thousands of structures. So how you can modify that? For example, if you have a reentrant here, so in the corners I can include a circle like this. So in this junction point I can include a circle like this, so you can evolve a new geometry. And even in the star I can include a triangle like this, so you can invent a new geometry. So this oxitic material is keep on going based upon the requirements. It can keep on changing, but these are the conventional or the basic structures which use the negative Poisson ratio. So how these geometries give a negative Poisson ratio? These are also made with the conventional material like steel, aluminum, or kind of composites or kind of polymers. And how this material is different from the conventional materials. So here you can see an example. So this is the reentrant structure, and this structure on pulling, what's happening? It is following an expansion. So it is following an expansion. So what is happening in the conventional material? So if you pull something, this region get compressed or it will get contracted, whereas here an expansion is there. How this expansion is happening here? So we will see from here how this expansion is happening. So in this figure, as I told, there is an expansion is happening here. So I have magnified this image by only considering this inclined portion. So here you can see an inclined portion. So now I am showing an inclined portion alone. So here you can see that there is a momentum is happening here. So when you are pulling the material, you can see that there is an angle between these two vertical member and inclined member. And you can see that when I am pulling it, this angle is trying to increase so that this member is trying to lift upward. So by changing these geometric profiles on loading, you will have an expansion in the center. So this mechanism is induced by the mechanism of buckling and or bending mechanisms. So here you can see that if you try to bend it or if you try to buckle this member, you will have this kind of expansion. And this is a very common mechanisms. In your oxitic structure, you can either have one mechanism or it may be a combination of different mechanisms. So the second mechanisms involved here, it is the folded mechanisms, or it can be called meager folded mechanisms. So here you can see that. So in the unloaded condition, it will be nearly a flat condition with have a little kind of projections. On loading, what will happen? It will compress in order to have in this shape. So these folded faces have the provision or have the flexibility or have the freedom to move accordingly to the desired geometry. So this is the folded mechanisms. And the next one is the rotating mechanisms. So here you can see that this is an undeformed shape. So if I am applying a load here, or if I push or pull the thing, you can see that this part will go inside, which will form like this. So this is a rotating type mechanism. And the next one is the Quimble type mechanisms. Here you can see that it's in a very crushed way. You can see that in real-time example, I can explain this. Take a paper, you crush it, and just put it on a table or so throw it. You can see that after releasing the load on that, it will try to come back. So it is completely crushed on loading, and if you release the load, it will come back. So you can see that that kind of crushed way of the material deformation. So that can also be tailored in such a way where it can be used for a desirable function. So coming to here, let me continue the various advantages of this one. The first one is the variable permeability. So you all know about the permeability. Permeability, you will know in simple way. I can explain that the materials have a lot of holes, which can perform some applications. Okay, so even in your cloth, you have a permeability. You have a holes there, so that will help for breathing. So that the cloth is breathing, so you can that aids the breathing. So there will be an airflow between your body and the outer thing. So permeability you can find in a lot of applications. An example is the filter. So in the filter, you can see that it's a permeable membrane. So the foreign particle or the dust particle get filtered by there. So this oxitic structure can be used for doing the permeability function. How it is happening there. So in here, you can see that there are two pictures here. The top picture is a oxitic material, and this bottom picture is the honeycomb structure. So honeycomb structure is there. Okay, I need to highlight one thing here. So on seeing these various shapes of the geometry, some people may think that why honeycomb is not an oxitic material. So a lot of people might know that. Might heard about honeycomb structures, because honeycomb structure is also one of the recent structure applied in various applications. How these honeycomb structures, because of this lattice thing, it have a larger energy absorbing capabilities. So honeycomb structures, you can see that. So some people may have that idea why honeycomb is not an oxitic material. It is also having a cellular structure, as like you are seeing here, and it is also have a regular structures and periodically arranged. Why it is not happening there? So let me explain here. You can see that. So this is the conventional thing, and if you are compressing this honeycomb structure, that is the conventional structure, which is having the positive Poisson ratio. You can see that on compression, this region needs to be, it must be compressed or it must contract. But here it is expanding. So this is the reason why it is not considered as the oxitic material. Since it is a Poisson ratio is positive, so this material is not an oxitic material, but it is having a lot of similar features like the oxitic materials. Okay, so coming to this variable permeability. So here the conventional positive Poisson ratio honeycomb structure and the negative Poisson ratio re-entrant structures are compressed. Here you can see that on applying load, the expansion in X direction and Y direction is similar. For example, you can relate this with this coordinates present here. So this is the X and Y direction. You can see that on pulling, the area or the size of the hole is increasing both in X and Y direction. So you can reach from this shape to this rectangular shape. Okay, so when you are increasing that, when you are applying pulling direction or a pushing force over there, you will have a uniform increase in the void area in X and Y direction. So this is a very good property which can be used for various purposes. Whereas coming to this conventional, you can see that if I'm compressing or if I'm pulling it, you will not have the same fashion of deformation in the perpendicular or in the normal direction. So here you can see that, for example, if you take the center cell, the length of the length of the void in X direction and this length of the void in Y direction is different. So comparing to this conventional material, this oxitic material have some benefit on maintaining the same area in both directions or same length in both directions. So here in this picture, you can see that when it is highly compressed one, it can filter a material of this size. And if you are expanding more, there will be more void area will be created. So you can increase, you can filter the bigger particles. And if it is in full maximum expansion condition, you can filter the bigger particles. Okay. So when you are going to buy a filter, you might hear this word. The specification of the filter is designed by its permeability. Okay. Nowadays, we all know about the mask. You know that we have N95 mask, we have different type of mask. The difference between that thing is the filtration capability. So if you want to filter a small one, you apply a little bit of load to the oxitic structure. So you will have a small void area, so you can filter the very small one. And if you are going to filter a very big particle, okay, so you can apply some load to the structure, and the void area will increase, so you can filter a bigger shapes, bigger particles. Okay, so with the use of this variable permeability characteristics of oxitic material, this oxitic material can be used as the filters for various applications. Okay, so here in this picture you can see there are two filters made with this reentrant and the honeycomb structures. Okay, so the next characteristics, the beneficial characteristics of this oxitic is the indentation resistance. So what is indentation resistance? So indentation resistance can be related with hardness as well as can be related with impact. Okay, indenting is something you have a harder ram or harder material, and you are applying a force over a material, you can find a deformation. So that is the indentation. For example, if I'm applying a pressure, you can see that my hand is indenting inwardly, which means there is a deformation is happening in the inwardly. Okay, so this is the indentation. So in real-time applications, a material should have a higher indentation resistance. Okay, either it may be loaded in a lower load rate, or it may be loaded in a higher load rate. Okay, so in both cases, we need this indentation resistance. So this oxitic material will have a better indentation resistance than the conventional material. Okay, so how the conventional material behave and how the oxitic material behave. So we are going to see here. So the first figure shows that how a conventional material behave. So what will happen when this is a ball indenter. Just consider this is a ball with made up of some steel, and this is a rubber material. Okay, for your understanding. So just consider this harder steel ball is compressed, or it is indented against the softer material. So what is happening there? In order to accommodate this load, the material around this region, which I am highlighting with this pointer, will try to spread in these directions. So the material from here will try to go here. So even in here also you can see that. So this is a normal surface, and when I am pressing that, this portion is coming up. Okay, so this portion is coming up. This you might notice in various cases. So this is because, so in order to relieve the load from here, the material at this location will try to spread from this portion to this portions. In some of the manufacturing processes like forming, even some process like forging or some processes, this type of deformation is beneficial even in wire drawing. So the deformation of spreading of material will be beneficial. But in terms of indentation resistance, if you see in the point of indentation resistance or the better property of the material, that is a negative thing. I tell you the reason why. So here the material is spreading that. But on the other hand, if you see the oxitic material, here you can see that the material is trying to spread towards the indenter. So here it is spreading away from the indenter. So what will happen when the material is trying to spread away from the indenter? So the density of this material will be reduced, because here it is spreading and it is reduced. Whereas in this case, if a material is spreading towards the material, so here the density of the material will be increased. By that way, the amount of indentation will also reduce. So thereby, the oxitic material will offer a higher indentation resistance. Even in this picture, the schematically representation, you can see that here nearly a 1/4 of okay, not 1/4, nearly 1/2 of near the radius. The radius of it's indented nearly to the radius of the ball, whereas here you can see that the indentation level is very small. Even 1/3 or 1/4, 1/3 or 1/4 part is only indented from this surface. You can relate it with this the initial surface. So here, if I draw a straight line, nearly half of the ball is inside the material, whereas here only a little amount of the material is deformed because of this indenter. So this beneficial property is highly useful in high indenting applications. For example, if you are using this material for applications like helmet, this will be useful. And if you are applying this material in automobiles, this will be useful. And you can use in the defense applications, this will be useful. Okay, so this will be useful in many ways. And coming to this next picture, we can see that, so there may be a question may arise from you. So here, the indentating area in this direction, it's very small, whereas here, the deformation in this area is very bigger. So some people may think like, okay, so the oxitic is having a very big deformation in this direction, so it is a detrimental property. So it's not the case. I will let you know. So here you can see that if you are having a conventional material, okay, which is having the so this is not B, this is nu, which represents the Poisson ratio. So the Poisson ratio is greater than 0, so which is a positive Poisson ratio. So when you are having a positive Poisson ratio, you will have lower shear resistance, so which was explained in the previous slide. And when you are having a negative Poisson ratio, you will have a higher shear resistance. So here you can see that here you have a lower shear resistance, which allow larger indentation. Whereas when you are having a negative Poisson ratio, you have a lower indentation, whereas the area is bigger. This is because okay, this is beneficial in some way, because you can see that if a pointed load is there or a pointed deformation is there, you will have encountered a crack or something. But when you are having a wider bending or wider deformations, that cannot create a crack. So crack is a failure. So in that approach, if you see this property will be a beneficial. Again, I'm saying that you need to tailor these mechanisms in order to make it beneficial. So if I'm saying oxitic material, it is not a completely beneficial. You need to tailor that. You need to alter or you need to optimize the behavior in order to fit for your applications. So as I told before, so if you have a higher shear resistance, this will be also having an influence on creating an indentation resistance. So the Poisson ratio is associated with shear resistance, and the shear resistance is associated with the indentation resistance. And I will also say an example. You can see if you see an example, like if your car is crashed on a wall, okay, for example, you can see that you can find a kind of deformation, not a crack. So it will have a crushing or it will have a bending, but not a crack. So in that way, these type of things are very much appreciated. So the next one is synclastic curvature. Okay, so here you can see that the figure A is the conventional way of thing. You might see in many cases, if you have a paper, try to bend in one direction, the other two directions will try to lift up. So this is the conventional way of behaving. But whereas here in oxidic material, there is a possibility if by selecting the proper geometry and the geometric parameters, you can bring a regular form of dome shape. So this is beneficial for a lot of applications. For example, if you are going to apply a material for such a kind of applications, in this case, you can apply this for a helmet, you can apply this for a knee pad. So this is have a higher flexibility to deform to respective shapes. Okay, so just imagine if you want a shape of like this, what you will do? You can either go to additive manufacturing to create the dome shape, or you will go to some kind of plastic deformations like bending. You will go for some kind of machining to bring this shape. So it's very, very hard. But just imagine that if you are having this kind of oxidic material, so that have a higher flexibility to take to different shapes. So, and another application of this oxidic material, you all know about the shape memory alloys. So in the shape memory alloys, it can be deformed to some shape, and on loading or some simulating or some kind of unloading, it will come back to its desired shape. So that kind of application can take this oxidic material, since this oxidic material is having higher flexibility. Okay, so this is about this one type of application, and another type of application. This can be used for creating some kind of building structures. It may be either in the form of some polymer based sheets, or you can use this is for an aesthetics looks. So here you can see two examples of usage of this curvature to build some structures. So you can create a temporary or a permanent structures. So you need to tailor on that. Okay, so the next application I'm going to discuss, or the next potential of oxidic material, its energy absorption capability. Okay, so here you can see that there is a helmet. It's padded with the oxidic material. So we all know that we all have a helmet. We can see there is a sponge under the hard shield. So why we are having that? So that will offer some kind of cushioning effect. That's the first reason. The second one is it will also give the energy absorption capacity. So on loading or get impacting, if you fell down, it will get impacted over there. So it will absorb some energy over there. So that's why we are using a foam. So this can an oxidic be a foam? Yes, of course, oxidic can also be a foam. Okay, but not all the foams are oxidic. The only thing is the oxidic foam needs to perform negative Poisson ratio, but conventional foam, you need some kind of air voids or some kind of void region. That's enough for conventional foam. So here there is a study compared study by this author comparing the conventional foam with the oxidic foam. So here there are two steps were used, not two steps, two way of loading were used here. One is the helmet is trying to impact in the front portion, and it's impacted in the side portion, and the performance is measured in the using GAD severity index. So GAD severity index is nothing but it represents the extent of injury. Okay, so that means if the index is low, the injury is low. If the index is higher, the injury is higher. So this is the way of explaining that. Okay, so here the test was carried with different impact loading conditions. So here it's mentioned in the way of impact energy, and you can see the comparison between conventional and the oxidic material. So here you can see that the conventional material, in all the cases, it is having the higher severity index which means it will lead to higher injury to the eye. And if you see this dotted bar, which represents the oxitic frontal impact, the severity is lower, so which is a very good thing. So there are some kind of expansion and contraction happened in the oxitic foam, which absorbs the energy and results a lower impact to the guy. So this is a very good thing. And if you also see in the side impact, you can see that this oxitic is having the lower severity compared to that, especially if you see in this case, nearly half of the performance is improved. So the value is nearly 2 times bigger for the conventional thing. So this is a beneficial property. And next one is higher fracture toughness. So this is also an important thing. So as I told before, that this material can avoid cracking or can postpone crack propagation or can avoid crack initiation. So these are the terms related to the fracture toughness. So if a higher fracture toughness, there will be a higher resistance to cracking or crack propagation. So this is the idea. So how this is happening here? So in the conventional material, the less amount of energy is required to the crack opening. So you consider this is a crack, you have a gap here. So you, in order to propagate this crack to a bigger size, you need to open it. So on opening of this region, the crack will propagate. So for the oxitic material, the energy required to crack propagation is higher. So in that way, it offers higher fracture toughness. So here you can see there is a critical tensile stress. So there is a critical stress, it needs to be created in order to propagate a crack. Okay, so this have a relationship between the Poisson ratio. So if there is a Poisson ratio related with the critical stress, of course, we can tailor the Poisson ratio to negative and we can increase the resistance against the fracture. So in this figure, you can see that there is a schematic diagram showing the fracture toughness test. Here you can see that this is the initial crack used for the testing, and these are the two fixture region, and it will be opened. So here a loading condition fixture is there, so it can be opened. So here on magnifying, you can see that these are the potential regions which the crack can initiate. But in order to initiate the crack, you need to apply more energy in order to create a crack here. But in conventional machining, if you are having a crack, you will have a continuous material which is deteriorated in that condition, which will pave a way to crack propagations or initiations. Whereas in this case, since it's a cellular material, there are a lot of chances to reduce the crack propagations. And the next one is, so this oxitic material is also having a potential in the fashion industry with respect to the textile. So here you can see that you can have a different types of material. Okay, so you can see the different types of applications here. The first figure, you can see that there is a dress fabricated using this oxitic material. Okay, so this dress obviously having some kind of patterns which are highly aesthetics. When it comes to the textile industry, along with the performance, the aesthetic of the material, aesthetic of the cloth or the dress is a major thing. So by using this kind of different patterns over there, it will provide a good aesthetic to that. And in the second figure, you can see that there is a handband is there. Okay, so this handband is made up of some special type of polymers. Sorry, I don't know what is the actual polymer name. It is a special type of bilayer polymer. So you have a one layer in the bottom and another layer in the up. So this bilayer polymer, it has a special characteristics that if it exposed to heat, it will expand. Okay, we know that a lot of material have this property. Even if you heat the steel, the material will expand. But here this expansion is enormous in order to create the cell opening. So you have a lot of cells. When it is not in expansion conditions, it will be closely contacted. And when it is heated, it will expand. Okay, and the temperature used there, it's the room temperature. So if you wear this band during the summer, it will expand by reacting or by triggered through the environmental conditions. The cell will open. So if the cell will open, you will have a good breathing between your skin and the environment. So in that way, you can either use this material, this kind of clothes during summer as well as the winter. So in the winter, it will be closed since your temperature is very lower, and in the summer, since your temperature is higher, this material will be triggered and it will expand. And the next one is, it is can be related with textile, because we know that we are using a lot of sofa, we are using some kind of textiles, some kind of velvet cloth or some kind of cushionings over the chairs, sofas. So this is an oxitic material. This is a chiral type oxitic material. So this can be wearable over a chair, and it can be adjusted to the person's body type. For example, if a lean guy is there, it can expand according to have a comfortable sit. And if a guy is a bigger guy or he's a fat guy, it can go according with his size. So these are all some of the potential things of the oxitic materials. Okay, the next one is how these oxitic materials can be used for the defense. As I explained in the previous slides, it's have a good energy absorbing capacity since it's a cellular type. And how this is possible here, what is actually happening over there, we can see that. So in the defense, we can see a lot of trucks like this. So these are all the type of lightweight armored vehicles, which is used for used as an maybe carrying some kind of electronics unit, or it can be used as an ambulance, or it can be used as a faster transporting vehicle. Usually the armored vehicles are not a faster transporting vehicle, it will move slowly. So there are some specific needs are there. The vehicle needs to be moved very fast in different type of environments, like it needs to so of course the defense vehicles are not going to ride on the road. It has to be follow some ups and downs and lot of different environments. So there are some category of vehicles called lightweight armored vehicles. So in that kind of vehicles, you can use this oxitic material. Since this oxitic material or cellular material, the weight of the cellular materials is very less than the bulk continuous material. Okay, so this is one advantage. And second advantage is it is also perform good impact resistance or good ballistic resistance. So how it can? So here you can see that there are 4 examples or 4 conditions. The first one is the monolithic, which is nothing but the normal case. You are applying a normal plate as a panel for this fabrication of this lightweight. And another 3 cases are they are using the oxitic core, and they are this is like a sandwich. You have a small thinner plates in the both direction, and you are having a bigger sandwich there. So this sandwich, you have different variations of that oxitic cells, the parameters, geometry parameters. So here the angle between these 2 members is 60, then 50, then 30. So you can see the difference in the shapes of that geometry. So here you can see that when a ball is indenting, or you just consider this as a bullet. So if a bullet is indenting in the monolithic, you can see that it is highly creating a deformation. It's a very big deformation. But if you see here, by changing these dimensions, you can see that the deformations is highly reducing here. Okay, you may ask a question. Okay, still there is a deformation, and how you are asking the deformation is reducing. just imagine this, the top portion is facing towards the environment, and this bottom portion is facing towards a guy who is present inside this vehicle. So if you are using a single panel like this, so if a bullet is hitted, it will also injure a guy who is present inside that vehicle. But if you are using this panel, you see only an exterior damage is happened, but the interior, which is this, the bottom plate does not have any kind of any deformation is there. So this is beneficial for the armor application as well. So how this is happened? What makes this advantages over there? So here you can see that there is a reaction force. So when you are having a bullet coming with a higher energy, it will create some kind of force distribution there. Okay, so this red color line corresponds to the monolithic, and this dotted line corresponds to the oxitic material. So here this is the 0, and this is the positive reaction force, and this is a negative reaction force, like a tensile and compressive, just nothing. So here you can see that when you are using a monolithic, on the impact, it will create a reaction force which is huge in magnitude. Whereas when you are using the oxitic material, it will be highly restricted. So I can say, okay, even in the next case as well, it is measured in the other direction, that is the horizontal direction. Here also the solid lines have higher force, reaction force, and here you have a lesser reaction force. So we can say that by using this oxitic material, there will be a force decaying capacity is there. So just imagine, this is a very good advantageous property of oxitic material. If it can reduce the force, or it will decay the force, or it can decay the energy it received, it will be more interesting for other application also. Okay, for example, you can use this to arrest the vibration. You can decay the force and you can arrest the vibration. So it can be used as a shock absorber. You can use this as in an auditorium. So the sound is a wave. That wave can be decayed. So you can use as a vibratory arrestor. Then you can use for acoustic purposes. So this have many more potential. Okay, so far I have explained a lot of advantages about this. Then you may have a question. It was the publication start arising from the year 2000s. So now we are 2020, almost a lot of years are there. Still, why it's not have a potentials in various applications? Because there are some challenges associated with this. This is very important part of my presentation, because this will be useful for a lot of researchers or a lot of academicians. They can work on this as a project or some kind of proposal or kind of thing. So this is very important. So it's have a lot of challenges which deteriorates its applications. The first one is design complexity. As I mentioned in many of the slides, I told you that you need to tailor the geometry. So that means all the geometries are not showing a beneficial thing. So you need to optimize the geometry first, which means the shape of the oxitic material, as I explained, like reentrant, chiral. So you need to select the geometry based upon its mechanism, either it is a bending, buckling, or rotating, or what are the things. So first, it's a design complexity is there. Then after selecting the particular shape, you need to again optimize the geometry parameters over there. So like, for example, in this case, the length, the angle, the length of the inclined members, a lot of things. Then thickness of this strut. So there are a lot of things are there. So it's very difficult to design it. So based upon the applications, in the way of theoretical, not theoretical, numerical way of building these, or you are going for a manufacturing, you need a high skill about the mechanism, about this deformation mechanisms, everything. So you need a highly skilled person to do this, the first thing. The second thing is the manufacturability. So this is connected with the first reason. So since the geometry is very complex, it's very difficult to manufacture. So the only option, you can either go by machining. So the machining is possible for very simplified geometry, but for cells like this shape is very difficult. So there are the flexibility of the manufacturing capabilities are very limited. So most probably you should go for the manufacturing systems like laser, additive manufactured laser based additive manufacturing system, or electron beam based additive manufacturing systems, or nowadays we have arc welding based additive manufacturing systems are there. So you need to go for that. And even though if you go for that, you will have a lot of issues. For example, in this figure, I demonstrated a picture related to an additive manufactured these shapes. You can see that the surface finish is very poor. You will have some kind of micro pores, and you may have some kind of fracture surface, not fractured. Okay, on loading, it will initiate some fractures. So you can see that in this picture, you can clearly understand what is the problem when we are going for manufacturability. So you need a design optimization, then you need optimization for the manufacturing process as well. Okay, you need to optimize the process parameters in order to have that. So coming to the manufacturability, again you have a bigger challenges that you will have the cost related issues. So if you are using a laser beam systems, or if you are using electron beam systems, it will be very difficult because you have two problems. One is the powder handling problem, and another one is the manufacturing issues. So the powder handling is also very difficult, and the cost of the powder is it's higher than the bulk material. So these are all some of the issues. And when you are going for the machining, again you will have the heat generation due to machining is there. That will induce some kind of residual stress formation. Since it is a very thin structures, that thin wall will highly prone for the residual stress, and it will go for a ready failure. So these are the problems. And okay, so I'm talking in terms of the oxitic materials. If it is metal, okay, again, and another question, if it is a polymer, all the problem will be okay. Yes, of course, if it is a polymer, you can reduce lot of challenges over there, but the polymers will have a good elastic property, but in the way of strength, it's deteriorated one. And the second one is, in a long term, the polymer will not be a suitable one, because it will react to the heat or heat conditions. So there will be some forms of scales, or the property will be changed to the time to heat. So a lot of problems are there. So these are all the problems related to manufacturability. The next one is the material flexibility. That's the thing I'm talking about. You can only go for the polymer in order to avoid a lot of challenges. So in order to use the materials like steel, aluminum, so you need to come across a lot of challenges, as I discussed. The next one is stress concentration. So if you are using a metallic oxitic over there, again, there is an issue called the stress concentration, which is very important. Here you can see there is a picture showing used for the fatigue test. Here you can see that there are a lot of sharp corners are there, which have highly potential for the crack initiations, this kind of thing. So in one of the slide, I explained that it's having a higher fracture toughness, and here I'm conversely saying stress concentration. So you need to overcome this stress concentration in order to achieve that good fracture toughness. So by this, I'm closing my presentation. So these are the conclusions of this one. So the unique way of deformation of oxitic material, it's have high flexibility, adaptability to various applications. So you can tailor the geometry, tailor the material used for the geometry for the various applications. So there are a lot of chance to explore on it.
So I wish everyone to read about this more, because this is a very, very big topic, since it's the meeting consists of people from various streams. I used to explain in a very very limited way. I'm not going particularly to any of the in-depth things. So I ask you to look for, though you from different different streams of engineering, of course, this auxetic material will have some kind of applications over there. Even this can be used for some kind of piezoelectric material as well. So people from electrical backgrounds can also be used here. Even this material can be used as a heat sink, different heat sink in the electronics system. So in the electronic processor, the heat generation is a important thing. So this material is having a higher capability for higher heat transfer capability, since it's have a lattice, the airflow will be more. So by this way, the electronic peoples can also work. So there are a lot of applications are there. Biomedical research, a lot of biomedical researchers also going there. Even the heart stent, now people are using this auxetic materials over there. So this stent will have expansions in order to fit to that regions, and a lot of other ergonomics related biomedical research is also going there. Like I explained in one of the slide about the chair, with respect to different size of the people, it can accommodate it accordingly. So it have wider potential over there. So everyone have some take back from this presentation, I believe. So I'm inviting you to have a discussion or some queries with you from you.
Yes, sir. Thank you, sir. You can answer your screen, sir. Okay. Thank you, sir. Thank you. Thank you, sir. It was an excellent eye-opening for all of us engineers here. Really, the auxetic materials, really, who is a pioneer, sir, in this materials? In which country is pioneer? Country or any company like that?
Company, I think, to my knowledge, some people are having initiation. In one of the slide, as I told that it started even in the research very nearly. So I couldn't say that there is pioneer, but this NASA is working on this auxetic material. They are using this for some kind of applications, and some of the sports industries already made products, and it's available as a commercial things. So the sports persons, they produce some commercial products, but other field it's still in the research one.
The stunt material they are using,
all of us in this material. Really, it was interesting to note many of the developments in the auxetic materials. Thank you, sir. Thank you so much. Participants can ask questions to the chief guest. Any participants have any queries, you can ask.
Hello, sir. Good evening, sir. This is Professor Titus.
Hello, sir.
Sir, you have told some applications, and among these applications, in which application this material is more suitable, sir, for medical application or other than that?
If you ask me in that way, I can say that instead of field, I can say that this material is highly suitable for energy absorbing requirement in any applications. The main thing is energy absorption capacity. So if in biomedical, if you have energy absorption things, you can use it. If you have any other application, if you have energy absorption capability, you can use it. So I listed a lot of property enhancement by using this auxetic material. The thing is, among that various property, I can say that the energy absorption capacity is higher on this.
Sir, thank you, sir. But if it is having more energy properties, shall we use it for solar panels or for any power generations?
No. This is not like that. Okay.
Mechanical.
This is a mechanical type
Sorry,
of.
this is mechanical application for any material which is required for high expansion or high stretching areas, this can be used, you mean to say?
Okay, sir, fine.
Ah.
Then okay, sir.
It's an impact energy, sir. Impact energy. It's not
Okay,
like
impact. Yes, sir, you are right, sir. Impact energy.
Okay, sir. Thank you, sir. Thank you, sir.
Participants, if you have any queries, or else we'll move on to the next agenda. So, we move on to the next agenda. I'll announce the next week's program. Next week's program is going to be delivered by Dr. Sankar Goyengo, Chief Architect and WOW Factors India Private Limited, Faridabad, Haryana. It is going to be personal development. That is the topic is reframe yourself. I request all our members, other institutions, that is Indian Computer Institute of India, Touchability Chapter, Indian Institute of Welding, Touchability Branch, Indian Welding Society Southern Zone, Indian Institute of Metals, Touchability Chapter, and Indian Institute of Industry Engineering. All the institutions with your friends, you can participate and get benefited. Now moving on to the next agenda, I call upon Engineer Madhuramani, Chairman, Indian Institute of Industry Engineering, Touchability Chapter, to propose vote of thanks. Over to Engineer Madhuramani, sir. Madhuramani, sir. Madhuramani, sir. Madhuramani, sir. He's there, but he is not turned up. Now call upon Dr. Titus to propose vote of thanks. Dr. Titus, sir, you go ahead. Yes, sir. Madhuramani, sir, has come. Sir? Madhuramani, sir, please propose vote of thanks. Yeah. We are waiting for you.
So, on behalf of participant institution, our sincere thanks goes to Dr. Sri Sabari Shanmugam for taking much interest in explaining the properties, geometries, and uses of oxitic materials in different areas. So, arranging regular lecture programs with various professors and the field on different topics is a difficult task. Our special thanks goes to Sri Selvaraj sir. So here it is my duty to thank the office bearers, members of various participating institutions, that is IEI Trichirappalli Chapter, Computer Society of India, the Indian Institute of Welding, Trichy Branch, Indian Welding Society, Southern Zone, Indian Institute of Industrial Engineering, Trichy Chapter. Our special thanks goes to Sri Lakshmanan, Sri Karupasamy sir, Dr. Edwin Brown, Amit Chandra, Dr. Govindraj, Professor Titus, and Uma Sankar for actively participating in this meeting, sir. Thank you very much, sir.
Thank you, Madhuramani sir, for excellent vote of thanks. Thank you, Sabari sir. Really, it was an eye-opener all of us. Really, it was a knowledge kit on oxitic materials. We have got an idea about oxitic materials. Thank you for exposing all of us in that area. Looking forward to associate in future, sir. Thank you so much, sir. Good night to everyone. With the permission of everyone, we will close the program, sir. Thank you, Sabari sir. Thank you. Thank you.
Thank you, sir.
Good night, everyone. Good night, everyone.
Thank you, sir. Thank you, sir.
Thank you, sir.